Hi, everybody. This is Mr. Folly in ugly orange. Let me change that to beautiful gray. And welcome to me teaching you your formatives. So this is it. I know there's a typed out part already posted, but hopefully, if you have questions, this will help you. True or false? Assume particles cannot reach absolute zero. So solid particles move across each other. That's false. This describes liquids and gases only. Gas particles vibrate. I'll go with false on that. They shoot across each other in rapid, random, straight line motion. Solid particles never stop moving. That is true. Remember, the only time you stop moving is if you reach absolute zero. And this one says assume you can't. And really, they can't, but we can't get there yet. Attractions, intermolecular forces, in gases are stronger than attractions in liquids at the same temperature. That's false. If you're at the same temperature, the reason why you're a liquid is the love you have for your neighboring particle. And if you're a gas, the reason you're a gas is you have less interest in your neighboring particle. Solid particles have 0 Ke. That is false. That would only be true at absolute zero, but we said you cannot reach absolute zero. Gas particles have more Pe than solids at the same temperature. That is true. The difference between gases and liquids, or gases and solids, the difference between gases and solids is potential energy. Temperature is measured independently. Gas particles move past each other. That is true. Liquid particles move past each other. That is true. They both do that, but solids do not. Solids have a constant volume but variable shape. That is false. A solid keeps its shape. This describes a liquid. Gases have a constant volume. That is false. If something smells, it's a gas. It will expand to fill the entire room. Pull my finger. Liquids have a constant volume. That is true. If I have 30 milliliters of liquid and I throw it in your face, 30 milliliters will hit your face. Gases have variable shape because their bonds are weak and they spread out. That is true. Not that their bonds spread out. I suppose that's bad writing on my part. The they would be the particles spread out, but gases have variable volume because their bonds are weak and they spread out. Hey, that's also true. I guess variable shape wouldn't really be spreading out, so I'm going to change my answer here to false. But but they are weak and they'll spread out because of that. So variable shape. I guess spreading out doesn't mean getting bigger volume. They're just changing their shape. Solids have constant shape because their bonds are strong and the particles don't move. That's a false. Particles do move. They only vibrate. Vibrate. Kinetic energy changes during phase changes. False. That's potential energy. Potential energy changes during phase changes. That's true. Potential energy increases during melting. So remember, I had solid, liquid, way up here is gas. So potential energy increases during melting. Melting is solid to liquid. That's increasing. That's true. Potential energy decreases during boiling. Boiling is liquid to gas. It doesn't decrease. That's false. Kinetic energy is essentially bond energy. That is false. That is potential energy is essentially bond energy. Oh, come on, erase. Come on, erase it. Doubling the average kinetic energy of particles doubles the motion of the particles. Oh, sure, we'll go with that. Water boiling for 2 minutes has the same temperature as water boiling for 10 minutes. That's true, and we don't even have to watch water boil for 10 minutes to know what's temperature. 98. What's temperature? 98. What's temperature? 98. What's temperature? 98. What's temperature? 98. Stable mixture of a solid and liquid indicates the temperatures at the melting point. That is true. A stable mixture of solid and liquid indicates temperatures at the freezing point. That is true. Remember, two states of matter are always at that point. Gases fill the container. That is true because they have weak bonds. They spread out, fill the container. Variable volume. Liquids fill the bottom of the container. That is true. Solids fill the top of the container. That's nonsense, silly talk. Adding heat always increases temperature. That is false. Not during a phase change. Increase of potential energy always changes the state of matter. That is true. For us. Potential energy you learn in physics is the energy of position. So technically, if I have a pot of water and I pick it up higher, it's got more potential energy. So I'm going to say increase in potential energy always changes the state of matter. I'm going to go with true for that, but I'm going to say Mr. Foley wrote that question and he does not like it. cooler to 80% water and 20% ice is warmer than is cooler to 80% ice and 20% water. That's false. If you've got a mixture, again, whenever you have a mixture, the temperature is that point. Melting loses, so again, I'm going to do solid, liquid, gas. Melting, solid to liquid. Loses PE, that's false. It gained PE. Remember, I like to give it the numbers 5, 8, and 100. Melting gains kinetic energy, that's false. When you change state of matter, PE is what changes. Boiling increases KE, that's false. Kinetic energy is essentially temperature. Boiling is yeah. Oh, it took part of my F. All right. Identify what is happening in the graphs below. More than one choice is possible. I'm going to change to a thicker pen. So this right here is a solid cooling. Maybe I'll solid cooling. No, it's a liquid cooling. Liquid, cool, and then it's going to freeze. In between is a liquid. Heat is being removed, so that means it's going from a gas to a liquid. So that is going to be condensing. Hotter than boiling, so that's going to be a gas. Cools, and then it's going to condense. This one is just a solid getting warmer. This is a solid getting warmer. This is melting. This is a liquid getting warmer. Solid warms, melts, liquid warms. All right, this one, it's between melting and boiling, so that's just a liquid. Cool cats. Oh, what a monstrosity here. Starting down here. I'll start up here. Solid warms, melts. Here's the liquid part. Liquid cools, boils, gas warms. Okay, so now I'm going to go to a smaller. I'm regretting my enormous markerness here. Go to a more middle one here. What equations can be used to calculate this? So 33. I'm just going to write it right up next to it. 33. I'm going to change my color though. So liquid cools and freezes. That's going to be MC delta T plus M delta H fusion. This is always change in temperature. Slant T is change in temperature, change in state. 36 is just M delta H. It's the high one, vaporization. This one, start with a gas, so I'm going to do MC delta, whoa, MC delta T for the first part right there, plus M delta H vap, and it's vaporization because boiling is the gas. This one is just a solid, MC, I'm going to put a little S for solid, delta T. I'll start labeling my C's from here on out. So for 35, that's a long one. I have MC solid delta T plus M delta H fusion plus MC liquid delta T. This one right here, I only have a liquid change in temperature, so I have MC liquid delta T. This one's the monstrosity. MC solid delta T plus M delta H fusion melting plus MC delta T, that's a liquid, plus M delta H vap for the gas, plus MC delta T gas. Oof. All right. Oh man, I almost lost that. All right. Keep on moving. Well, I lost that. More true and false. Melting takes as much energy as boiling per gram. That's false. Boiling is way more. Why? Because there's the difference in solid to liquid bond energy is much less than the difference. So it's not that Gases have so much more energy. The difference between a liquid and a gas. Gases are as condensed as solid. That's false. Gases are the only uncondensed state of matter. The change in distance between solid and liquid is much less than the change in distance between liquid and gas. That's what I was talking about before. Change, I used the word difference before. Delta H vap is always greater than delta H fusion. That's true. Why? Because the difference in this. Delta H vap is energy to boil or condense. That's true. Small c means temperature changes temperature slowly. That's false. Small c means it changes quickly. Remember, metals have a small specific heat. A large C is a substance that is an insulator. That's true. Metals have a large C. That's false. It takes a lot of energy to change the temperature of a substance with a large C. That's true. Okay. All right. Here's the mean ones. If you haven't done these before, what is the specific heat of the following if data was collected like in our lab? So we have metal equals water, and it's going to be MC delta T equals MC delta T. So the mass of the metal, 25.5. Specific heat of the metal, which is what we're solving for. Change in temperature of the metal goes from 100 to 33, that is 67, equals mass of the water, 10. Specific heat of water is 1. Change in temperature of the water goes from 10 to 33, that is 23. I'm going to grab my calculator. Okay, I have my calculator now, so I'm going to do 10 times 23 divided by, 25.5 divided by 67. C equals 0.135 calories per gram degree Celsius. If you have a hard time going from here to there, talk to your math teacher or talk to me. I'm happy to tell you how to do it. Same dealy-do here. So I'm going to put my metal on the left. MC delta T equals MC delta T. And just remember this, I'm going to put H2O here. And I'm going to put metal here. Mass of the metal is 25. Solving for the specific heat of metal. Change in temperature. Initial temperature of the metal is 100. Final temperature is, 77. Mass of the water, 65. Specific heat of water is 1. Delta T is from 100 to 20, which is 80. Calculator time. 65 times 80 divided by 25 divided by 77 is, that's a big one, 2.70 calories per gram degree Celsius. That's not very metal-like. I've got one more, so I'm going to do it a little slower. Okay? So what's going to happen is the hot metal is going to equal the cold water. Okay? So I'm going to, we know these things are going to change temperature, so I'm going to have MC delta T. That's changing temperature equation, is MC delta T. So remember, this is the hot metal. So M stands for mass, which is the mass of the metal. C is the specific heat of the metal, which is what we have to be able to solve for from the lab that we did. The change in temperature goes from the initial hot temperature of the metal down to the final temperature of them both. Remember, these two will both be the same final temperature. So 100 minus 28 is 71.9. Now the water is going to be a little different. So I'm going to look at the mass of the cold water, 15. Specific heat of water is 1. That's given to you, but you probably have it in your head by now. And I went from 20 to 8.1. That's 8.1. So now if I'm solving for C, I'm going to have 15 times 8.1 over 75 and 71.9. Just remember, the things on the bottom, you divide, right? So 15 times 8.1 divided by 75 divided by 71.9 is 0.0225. And don't forget the evil units of specific heat, calories per gram degree Celsius. All right. So this last one gets a bit even meaner, although I think I have two of them. Yeah, I've got two of them. Finding the final temperature is pretty much the same, but we've got to be very, very careful because now we really have to focus on our negative hot equals cold. Before we had something that would work out and make it a little better. But what is the final temperature of a mixture of 18.5 grams of water at 30, mixed with 39.5 grams of water at 45? So 45 is the hot one. So I'm going to have negative MC delta T equals, I'll put the parentheses for now. Oh, I'm not going to do delta T. MC parentheses T sub F minus T sub I equals positive MC T sub F minus T sub I. So the mass of the hot one is 39.5. Specific heat of water is 1. The final temperature. What is the final temperature? That's what I'm looking for, T sub F. The initial temperature of my hot one is 45. That's the bigger number. Minus 45 equals the mass of the cooler one, 18.5, times specific heat of water, which is 1. T sub F is what I'm solving for, minus 30. Okay, so I'm going to do my distribution here. So it's going to be negative 39.5, negative 39.5 T sub F. Again, negative 39 times negative 45 is going to be positive. So negative 39.5 times negative 45 is going to be positive 1777 equals 18.5 T sub F. I'm just distributing times to each of them, minus 30 times 18.5 is 555. Okay. So now I'll put the T sub F's on the left. So negative 39.5 minus 18.5 is negative 58 T sub F's equal, got to move my monster number there, negative 555 minus 177.5 is negative 2332.5. Now I'm going to hope and pray that my temperature ends up between 30 and 45. Let's see here. That answer divided by negative 58, 40.2. Whew, it does. Okay, so again, we're going to start with MC delta T equals MC delta T. Got to have my negative, right? And then make sure you match up your hots and your colds and be careful with your algebra, and then you're okay. Last one, see if we can get it before the bell rings. What is the final temperature of a mixture of 225 grams of water at 12 with 25 grams of water at 95? So negative hot equals cold. Negative MC delta T. Not delta T. MC, parentheses. MC parentheses T sub F minus T sub I equals MC T sub F minus T sub I. Mass of the hot, 25 grams. I'm going to leave out, well, that's one. Might as well put it in there. T sub F minus 95 equals mass of the cold, 225. That's a lot more. 1. Final temperature is what I'm solving for. My initial temperature was 12. All right, so now I'm going to distribute. Negative 25 T sub F, negative 25 times negative 95. Negative 95 times negative 25 is positive 2375 equals, so long people, 225 T sub F. You can stay till the end of this if you want. 225 T sub F minus 12 times 225. 12 times 225 is 2700. So now I'm going to collect my T sub F's on the left. So I'm going to subtract 225 from there. So negative 250 T sub F's equals, going to subtract negative 2700 minus 2375. It's 5075. Negative 5075. Hoping my temperature here, Negative 5075 divided by negative 250 gives me a number in between, and it does 20.3 degrees Celsius, and we got it all done in 20 tools.